thanks for joining. Super excited for this one. I want to welcome our good friends from MongoDB, Matt and Ashwin, to talk through their journey towards application-driven intelligence. Thank you. Take away.
Thank you. Thanks everyone for coming along to our session. My name is Matt. I'm part of the product team at MongoDB. I'm going to kick things off briefly by talking about what app-driven intelligence is before passing over to Ashwin, who will handle the majority of the session, and there he's going to show app-driven intelligence in action with a joint solution, a joint demo he's built, powered by MongoDB and Databricks. Before getting into any of that, you may ask, why is an OLTP database vendor presenting at an analytics and AI show? We're not here to try and convince you to replace your data warehouse or your data lakehouse. Those are very different technologies doing very different things, to which MongoDB is complementary, not competitive. What we do see, however, is that developers, who are the primary users of MongoDB, they're our design center, that's who we build for. Developers increasingly are working to bring intelligence into their applications, whether that's surfacing insights, taking autonomous action on behalf of the user, engaging users with natural language, and doing all of that with fresh data in real time. And that for developers does two things. Firstly, it means they've got to start to collaborate and work with data teams in ways that perhaps they haven't worked previously. And number two, working with tools and technologies that they may not have been so familiar with. And so what Ashwin and I are hoping to do in this session is present to you an approach and a platform which brings together developers and data teams to innovate on this next generation of intelligent applications. So to dig into the agenda a little bit more, just so you've got a clear idea of what's going to happen, I'm going to cover the first two bullets you see on the slide. That's going to take another 5 or 6 minutes, pretty brief. I'll then pass over to Ashwin, who's going to dive into the demo, showing retail architecture based around personalization and dynamic pricing. Now, prior to Ashwin joining Mongo last year, he was a data scientist working in retail. So he brings a lot of domain expertise. But don't worry if you're not from retail, because everything he's going to cover is going to be applicable, right? From concepts to code, it can be transferable to other use cases. So most of the session will be focused on that. I'll come back up, talk about how to get started, and we'll leave 5, maybe 10 minutes, depending on how we get along for Q&A. So that's the running order. So firstly, defining app-driven intelligence. Why are organizations investing in it now? And we really see it through two lenses. Firstly, the desire to build smarter applications that can better engage users by taking intelligent action, engaging them in natural language, being able to run contextual-aware semantic search across vast troves of corporate data. So that's really about deepening engagement, out-innovating competitors. At the back end of that, the second major lens that they're going through is to really automate decisioning, to be able to react and respond in real time as data changes. So they can work on fresh data, take faster decisions, and higher quality decisions. So that's some of the why. How does it actually translate to real-world applications and use cases? And we've selected 6 here. These are all based on real-world MongoDB deployments, very often working in conjunction with partner platforms like Databricks. So things like retail, as we'll show today, personalization and dynamic pricing. Down on our booth, which is down in the expo hall, number 38. If you haven't been down there yet, come and check it out. We've got some demos around payment processing and fraud. We've got a demo around insurance underwriting. That was actually built in conjunction with an application we built with Databricks for travelers insurance. So travelers insurance taking new policy applications directly off the web, then running it through a data pipeline powered by MongoDB, essentially acting as a feature store, serving those features into Databricks to make a decision on whether that's a policy they want to accept, or they pass it off to a human for inspection. But there are a number of use cases, from kind of generative AI, where a lot of people are obviously kicking the tires at the moment, evaluating that, through to more traditional, classic analytical AI. Now, while these use cases are all very different from very different industries, they do share some common required capabilities. So they firstly have to work with live application data. So this is data that's typically no less than a couple of seconds old, and it's not a static snapshot of data. This data is constantly being read from and written to by the application. So it's in a constant state of change. The insights and actions we're taking against this data have to be delivered within the application flow, so typically less than a second. They have to work at app scale. So, we're not running a few heavyweight queries to power dashboards. These are queries that are servicing thousands of concurrent users simultaneously, or maybe more. And the outputs are driving app automation. They're consumed by software, by models, by algorithms that are built by collaboration or in collaboration between developers and data teams. Now, these required capabilities, what these are doing is breaking down the traditional silos that have existed between the application, which is where data is being generated, and then the back end into centralized analytics systems, using ETL or ELT pipelines to push that data through. I'm not suggesting, just to make it clear, I'm not suggesting for one moment that what you see on the right, that centralized analytics, those long-running OLAP-type queries will move into operational systems. That's clearly preposterous. I mean, from a personal level, I've been around databases for a long time. I've worked for Mongo for 10 years. I was 10 years working with Oracle and MySQL before that. And really dating myself, I used to work as part of the VOS initiative at Sun Microsystems. VOS was Veritas Oracle's son, so called the three horsemen of the Web 1.0 build-out. Now, that experience means that I've worked with some really phenomenally good database engineers, and what they will tell you is that everything you do to optimize an OLTP query, to extract that last bit of latency, that last bit of throughput, is an anti-pattern when you're running long-running OLAP-type queries. And similarly, at the other end, everything you do to optimize an OLAP query is going to screw your OLTP performance. That said, there is a decent middle ground where you have a lighter weight form of analytics touching 10, 100, maybe a few thousand documents or records where you really can optimize an OLTP system to be able to extract insight, take action. And that's the class of analytics we're talking about here. So to bring analytics and AI into our applications, what is it that we need to do? Well, when we look at the developers, we need to be able to provide them with tools and APIs to build more sophisticated queries beyond the simple kind of CRUD operations that are perhaps typical in operational applications. We need to be able to enable them to push as much analytics processing down into the engine itself, so providing things like analytics optimized storage and indexing, so they don't have to do all of that stuff back in application code. And we need to provide them with very simple, high-speed programmatic API access and connectors into models, into MLOps platforms, and other parts of the data ecosystem. But we can also start to bring our data teams with us in this journey into app-driven intelligence, so we can provide them direct access to application data, albeit that data is raw and messy, it hasn't been neatly curated. We need to give them the familiar tools and skills to do that, so invariably means working with SQL, of course, and we need to do this in a way that's isolated from the live application so they're not screwing and compromising user experience. And so, when you look across the spectrum of operational OLTP databases, there's a terrific amount of innovation happening in this space. Whether you look at the relational side, the NoSQL side, a lot of vendors are now thinking how they get to this. Now, obviously, I'm from MongoDB, so I'm going to present MongoDB's point of view. From our side, we have invested a lot of R&D over the past couple of years to really build out our capabilities to do this. And so it revolves around MongoDB Atlas, which is our fully managed multi-cloud database service for MongoDB. And the theory behind Atlas is to take our core OLTP database platform and augment it with real-time analytics capabilities, but putting those in the hands of developers in ways that fit their languages, their frameworks, their workflows, to make it very consumable to those developers. So to give you some examples, just to give you a flavor, I'm not going to go through everything you see on this chart, but things like the aggregation framework allows developers to compose very powerful multi-stage data processing pipelines where they can aggregate, transform, enrich data, essentially pre-process it for more sophisticated analytics engines for model building or inference. We can provide lightning-fast access to that data through row and columnar storage and indexing. So whether you're running highly selective queries that need to access a few rows of data, or high cardinality queries that are scanning across many different rows to try and extract insight from that, we take care of presenting that data and planning that data, whether it's a columnar or a row format. So again, that's abstracted away from developers. Last week, we announced Atlas stream processing, which allows you to take messages directly off a Kafka topic and continually process them in memory without ever having to land them into a database. So for very low latency, things like fraud detection or some IoT applications, you can do those things in MongoDB now. No self-respecting data platform is going to survive without vector search. So we also announced vector search last week, a long way ahead of Databricks, who announced it yesterday. But everyone is building out vector search. So with vectors, we can take our source data, our core operational data, and store that alongside our vectors, our embeddings, our vector embeddings, our chunks, our metadata, all in one storage layer, all fully synchronized, all accessed via a single API. So it's really putting a lot of these very powerful streaming, data in motion, as well as data at rest analytics capabilities into the hands of developers in ways that they consume easily. But because MongoDB is a distributed database, we can also open that up to data teams. So we have dedicated analytics nodes where they can work in complete isolation from the operational side of the app, using Atlas SQL so they can plug in their existing SQL-based tools, and using things like Atlas Data Federation so they can simplify data engineering. So companies like Coinbase, for example, do all their transactional work in MongoDB, and at the end of the day, they write that out as a Parquet file using Atlas Data Federation straight into Delta Lake. So it's a very tight, easy way of integrating. So examples of some engineering teams that are taking advantage of this, someone like Bosch, one of the world's largest engineering companies, also at the forefront of the IoT. For the past 2 decades, in fact, again, I'm going to age myself again, but long before it was called IoT, it was called machine to machine, and that's exactly what Bosch do. So Bosch are taking data from millions, tens of millions of connected devices and assets out in the field. They bring that into the IoT suite, their packaged software, with MongoDB at their back end, providing those insights and extracting analytics from that data. So that just gives you a kind of flavor of what we mean by app-driven intelligence. What I want to do now is pass over to Ashwin, who's going to talk a little bit more about the tight integration we have with Databricks, and then showcase some of the solutions we've built around that. So Ashwin, over to you.
Thank you, Matt. Yeah, that was, I think, a good introduction as to what's the data platform that we have, the various capabilities, and let's try and use it in a specific use case. Before that, firstly, MongoDB and Databricks talk to each other in these 3 particular ways. So firstly, if you have a streaming app, if you have some sort of batch, micro-batch, or real-time data, so you could use the Spark connector or the Kafka connector to basically transfer data from MongoDB to Databricks or back. So with the Spark connector, basically, you don't have to really move the data from one place to another, wherein you can actually process the data in real time in the basically from the collections where it's being generated. And suppose you collect a lot of data over time and you have historical data and you want to move this, different representations of this data as a materialized view in Parquet formats into various object storages, which is cheaper and better to manage and can be used for training various ML algorithms or doing analytics for historical information, right? You could use the aggregation pipelines and the batch out. So these are some of the ways we integrate with Databricks, and you could use all the analytics on Databricks for the real-time applications that you're serving through MongoDB. So I'll basically cover a demonstration in retail domain specifically for the reason that retail domain has a lot of these operational yet analytics challenges at various parts of it. So for example, retail challenges right now are omni-channel, being present in online or store. So basically, you want to give a seamless experience between the two of them. At the same time, they want to personalize what you're buying, what you're looking at various places. And also at the same time, basically, all this information needs to be accessible and very easy to be found. Like if a product is said that it's available at a specific store, and if I go up there to try and buy it, it should be available for me to purchase. So making all that available has multiple architectural challenges, like for example, multi-tenant, stream processing, and you need to have a full text search to, to basically surface this data to the user. So in the present architecture that we're going to be presenting, so we'll be basically covering various aspects of these. So in this here, you can see that we have broken it down into 3 segments here. So one is the source, where you will be generating clickstream data from your search listings pages, which is the search page, product listings pages, or the description page. And you'll be collecting data from multiple of these sources, right? You'll have merchants' pieces of information, you have competitor information, you have stocks or inventory with respect to how your warehouses are stocking them and so on. So you collect multiple of these sources of information and then try to build a collated view of this information upon which you can build search indexes to serve your mobile app or your web app. So in this architecture, what we are trying to do here is, all these sources of data that is being generated, we are basically transforming this data through workflows in Databricks in a way that, in real time, we are able to update the status of the product or transformed view of the product into a corpus collection which we create, upon which we are going to create a Lucine's full text search index. So that's one of the solutions. Another 2 solutions are that in order to have that competitive edge, we are trying to build a business intelligence score on the clickstream data in real time. And the second thing, in near real time, and also we are going to try and do a dynamic pricing use case wherein we can see that we log clickstream information and what the product was priced at when the purchase was happening. So you can do some sort of price elasticity on that product to identify how the product is changing over time, and so you can give a discount on that product so that it becomes more attractive for the user to buy it. So let's look at these use cases in a real demo. So we have a very simple app built out like this. So as you can see, I have some featured products here. So this is the products that basically right now are not selling for me, but I want to basically give out very high discounts and I want to basically promote them. So these products are coming with the fact that this price elasticity is a negative, and I have given up huge discounts, and I've tried to basically showcase it on the top of the basic page so that it becomes attractive and buyable immediately. So as you see it, you buy it. So we have also powered a full text search using MongoDB with this, the autocomplete as well as the searching and discovering of products is also powered with the Atlas search by creation of full text search index itself. So you can basically look at products, purchase them. So let me take one of the products here, right? So I'll just quickly grab this ID. So why I wanted to do that is, to showcase you the exact flow in how the things were happening in the architecture, suppose I wanted to add to bag this particular product, and I can see that the product is added to the bag and it's available. And so as soon as you did that, so this product was sent to the click logs through the Kafka sync connection. And I'm just listening to that specific topic here in the Kafka so that the product is getting pushed to Kafka and then to MongoDB. So I can see that this product has been added to cart and this is an event. Similarly, if I go ahead and purchase this particular product, another event is driven wherein I am basically trying to purchase the same product. And so this seamlessly gets listed. I mean, the changes are captured in the collections for the events that took place. And you can see that this particular product has 9 products left, 9 objects left in the collection right now. So let me get rid of this. So there are 9 left for this particular product in my inventory at this point of time. So let me go ahead and I just wanted to purchase 10 of these particular products. So I go ahead and place a purchase for 9 of these products, and hence all 9 products that were in the inventory right now are all gone for me. So I have made this purchase, and that's immediately getting reflected in our collection, wherein we can see that the product is out of stock and the available to promise flag is also set to 0 in real time. So this suite seamlessly basically updates the relevant collated collection that I was talking to you about, which basically collates across various facet fields that you want to create, as well as the display fields or the image fields that you store, right? So you can see that this product basically updates itself, and in real time you can surface to the user that this product has gone out of stock, and if you went back to your search page, this product is sold out. There you go. So let's actually, in a similar thing, let's actually see a use case of a vector search and how it can help. So I basically type out a query called handbags here. The query handbags is basically a case where it tries to, in a full text search use case, right? We look for the words present in the specific products. It's basically searching based on the textual terms that are present on the query. So we don't carry a lot of tan handbags per se, but we do carry a lot of tan colored other products, and hence we see undesired or products that the user might not purchase on that specific query. So that's where we can use a vector search basically to improve the results by re-ranking the products along with the vector similarity that we can do. So what's happening here is, on the query handbags, I'm using a transformer to convert them into a vector, and against each of these products, I'm also storing a vector basically representative of that particular product's facets or the display information that we are already showing to the user. So right now it's only using text transformer, so we have only the textual information around the product being stored here. But this could be done for the images as well as, and you can power image searches. There's umpteen number of possibilities with vector search that you could do, but this is one such example where we are trying to re-rank products and show that you are getting a more desirable and products that you might probably make a purchase with this kind of use case. So the prices that you see here are different from the prices that is what the original product price is. So how do I know that? Basically, you can clearly see from here that I have a discounted price against the product, which is the product price that I'm displaying, versus the actual price of the product. So how we go about this use case is that, so like I said, in Databricks, we have set up a pipeline, which basically is broken down into 2 stages here. So what we do here is, this is a scheduled job, which basically runs across the clickstream information and pulls in the information, pulls in the right information, builds a model based on price elasticity to calculate the discounts in real time. So this is a model this is a workflow that you can run every few hours so that you have collected enough amount of clickstream information in order to price the product right. So thereby you're incentivizing the user if a person is showing interest into purchase, but he's looking at the price and not making the decision. Multiple people do that. You recognize that this pattern exists. You can actually take action on that, and you can price the product right so that it starts moving and you don't have it in your inventory for a long time and wasting inventory space, for example. So what we've tried to do with MongoDB here is that, so the aggregation pipeline written here is basically trying to prepare a materialized view of the data that I could directly use in my ML modeling activity. And so as soon as so we are using a batch read here with the Spark connector, wherein we're pulling in the data along with the pipeline to get this particular materialized view. And this particular materialized view, basically, we would go ahead and train the price elasticity based model. So cross price elasticity is done across products, but in this case, what I'm trying to do here is I've taken the same product across different points in time, so that product probably yesterday and the product status today, and then basically trying to maximize the price elasticity so that I can identify the right price I can give for the product. So if I do this for enough number of products from various categories, I can basically predict a price, and using that price and the features of the product, I can build a random forest regressor model on top of this data so that I can predict the same for the other products given the pieces of, the features show up on the specific product. So in this particular workflow, I just train the model with using MLflow, MLOps framework, and I push this model into staging environment. And in the second half of the workflow, this is probably something that we'll probably run more frequently. So we can have a stored sort of a scheduled trigger function in Mongo, wherein you can run the pipeline to basically update your processed view of the clickstream logs, the materialized view that I just showed you. And you can then run this notebook in a more continuous fashion, which will basically pick up products that have, listed in that particular collection and then tag them with the model. So you can apply the model instantaneously and then basically apply a suitable discount against that product and push it back into MongoDB. Now, this is one of the workflows. A similar workflow is there for business intelligence core as well. I'm not going to go in detail. So this code is available on GitHub. You can always set this up yourself and try it out for yourself. And you can play around with this data and the code so that you can get a fair hands-on experience of how things are working. So I'll just move on from here and just try to show you. So I'm running this real-time Spark streaming jobs, wherein I'm listening to multiple collections in MongoDB, such as the available to promise, the predicted price that I'm predicting, the product description, basically the inventory changes that I was talking about, like if a product title changes or image changes or any other information, right? So I'm basically listening to multiple of these, like I said, ATP, images, and so on. So these are streaming opening. So basically, I have opened a Spark streaming connection between MongoDB and the Databricks so that any data changes that happen on the collection, the respective collection, would come into the data frame here, and I can suitably take a transformative action on top of that data and then republish it back into my final catalog collection, where I'm building my search index to power the UI that I just demoed to you. So this is basically, listening to all these specific connections and then pushing the data in real time. So it's basically sort of assimilating the data, transforming the data, and pushing it to the final collated view of the collection where the search index is getting built. So yeah, this is all I had. So, but I'll just walk you through how the search indexes are built, just in case if you are interested with how you can build your own search. Yeah, sure.
Firstly, thank you for this demo and talking about the vector search as well, because I have been dealing with this. So as you know, when we are talking about the search parameters, right? So when we render from any mobile devices, we face the issues with the Atlas, right? I think this is a common feedback. So these vector search, right, what you just demoed, is it going to address that problem as well? Though I don't believe that's related to the data management.
Sorry, you could repeat yourself for the last part?
Sure.
Yeah.
So basically, whenever we deal with the search, right?
Yeah.
Especially, suppose you were searching on the basis of the product,
yes.
right? The exact website, what you are showing from the laptop, right? Instead of that, if you just take it from .m version, means the mobile version, right? Then we face some issues to do the similar kind of search. So the particular search, the vector search, whatever you explain, is it going to solve or is it going to address in any way to that as well?
So the problem that I see with mobile devices is you show very few products to the user. So it's one product at a time. So you need to scroll. Is that the use case? So the way we have applied vector search here in this particular use case is that we are trying to discover products using the textual search and re-rank the products using the vector search as one of the signals to this. So you can have multiple other signals contribute to your scoring logic in the aggregation pipeline, the search aggregation pipeline. So I wouldn't say vector search alone solves that problem. Vector search, yes, contributes a lot of adding relevancy through semantic similarity, but you'll also have your business logic and other intelligences that you would have built on top of textual search, which would be
at the app level, you mean, right?
Yes, at the app level, which would contribute to it. So like, for example,
but the ranking one will help definitely over here,
yes,
right?
So the ranking here is not just based on the vector search. So I'll just quickly, the code is not readily available. So what happens here is I basically use the vector search similarity score. The price elasticity being negative is a very important factor for me to show it on the top, so that people in the retail space generally try to purchase from the top N items. And you can see that the 98, 99 percentile of searches end up in the top N results, which is much lesser than the actual recall of products. So that's when basically you take benefit of pushing these kind of products to the top. So the idea here is, so the pricing, price elasticity, and the business intelligence score that we calculate on these products, along with vector search, is pushing, re-ranking these products so that we are driving business intelligence in real time.
Perfect. Thank you. Sounds good. If you don't mind, I have another question. All right, sure. Thank you.
Sure, I'll just finish up. So I'll not take a lot of time here. So basically, I just wanted to show off how you can basically spin up your own vector index. It's very straightforward. You can just declare it in the mappings in this particular fashion. So I'm using a 384 dimension vector. You can use either Euclidean dot product or Euclidean similarity, and the data type is called vector, KNN vector at this point of time. So the idea is to support more in the coming future. But once you have this, you are basically, you can do your vector search with this in place. And the indexes are updating in real time. So as you add the products, it basically gets indexed, and that is also covered with this use case. So going back to my demo, so we wanted to, with all these features, right, it becomes very apparent that MongoDB is a very good online feature store. So why I call it an online feature store is basically we have different kinds of features that we compute while doing an ML modeling activity, right? We have static set of features. We have real-time features that we would want to use at the time of inferencing. So the static set of features don't change immediately, but they change over a period of time. And that's where basically MongoDB's developer data platform helps you build these views and store these views in MongoDB to be readily servable at the time when you need it. And preparing the materialized view was one of the examples that we just saw. So you can build such views and store away such views, which are for the static data views. And the real-time data that you basically compute in conjunction with these static data views, you can customize your ML flow PyFunk wrapper that you have for prediction. and then you can consume this piece of information for inferencing in real time. So that's where MongoDB can act as a very good online feature store. Getting into the specifics, right? So basically, we also have a Spark function, which for if you don't have a real-time need on the data, so you can also basically have batch operations where you can tag data and store data back into the inferencing as a batch job as well. So that's more about what I had. Yeah. So.
Thanks for coming along. I know you had a big choice of sessions you could have gone to. Just to wrap up, just very briefly before we get to question and answer, we do have, Ashwin and I are going to be down on the MongoDB booth, number 38. It's by the theater number 3 down on the expo floor. So we'll be down there this afternoon for the rest of the session if you had questions and wanted to come down and see some more of this stuff in action. All of the code that Ashwin went through is available on GitHub. All these slides will be published. You'll be able to get hold of that. Using that as a starting point, you see the notebooks that have been created and the various other code artifacts that have made up that demo. So hopefully that's a good start just to kind of spark your own imagination. We also have some other assets, white papers and things like that, that can talk at a more kind of business level around what app-driven intelligence is and why that matters. So with that, we really like to thank you all for coming along, and we'd open it up for questions.
Yeah, awesome. Thank you, MongoDB. It's just a great example of partnership and online feature benefits of Mongo. So anyone who has any questions, raise your hands.